All right, good afternoon. My name is Hosea Siu, and I'm here today to present to you my thesis, which is the effects of Earth encounters on the physical properties of near-Earth objects. I'm advised by Professor Rick Binzel and Dr. Nicholas Moskovitz, who is in Lowell, Arizona. So I'm tackling two problems in this work. The first is the scientific question of how near-Earth encounters affect the physical properties of near-Earth objects. And the other is more of a technical question of how do we streamline data processing so that we can sort of tackle problems like this in a more efficient way. And I'm going to talk about these things in reverse order because you collect the data before you analyze the data. But you'll find out later that there's a bit of a caveat to that. So I'm going to be talking about this in sort of four sections. First, we're going to talk about the background to this problem. And then we're going to go into the automated light curve fitting. This is the data collection and data processing portion of this. And then we're going to talk a little bit about the Earth encounters and the effects on NEOs. And finally, we're going to conclude and talk a little bit about the future work that can be done with the processes that have been developed here and the different things that we've analyzed. So first, as a bit of background, a number of different surveys have looked at just asteroids in general and NEOs in particular. So first, in order to figure out what it is you're looking for, there are discovery surveys such as LONEOS, Linear, Catalina, and Pan-STARRS. Basically, look out at the sky and just ask the question of what can we see, what's out there that we don't know about. So these find different near-Earth objects as well as other asteroids. And then after we know about whatever objects are out there, other surveys go forth and try to characterize these objects, try to figure out a bit more about them than just the fact that they exist. Other projects like SMAS, IRAS, WISE, etc. Try to characterize objects in different ways, getting characterizations such as spectra, light curve, and albedo from them. Now, I'm actually helping out with a project called Manos, which is the Mission Accessible Near-Earth Object Survey. And this survey is specifically looking at the spectra and light curve portion of the characterization. I'm going to describe a little bit more about Manos in a second, but so basically just remember that these two are the things that Manos is considering. I am specifically only looking at the light curve portion of Manos, and my automation work is done only in the light curve portion. So I'm not talking about spectra at all here. So why Manos, if we already have all these surveys? Manos is important because it fills in a gap in our understanding of near-Earth objects. You notice here that in this plot of previously characterized NEOs, you notice this big bump over here of objects that are pretty low magnitude. That means low magnitude corresponds to bigger objects. Bigger objects are easier to see. Easier to see means that you can characterize more of them, which means that there's a big bump there. So in the past, we've basically been limited by the technology that we have. But Manos is able to push current technology to look a little bit further down the magnitude scale, look at dimmer objects, smaller objects, so that we can sort of fill in our understanding of what's going on with objects that are a little bit smaller than what we're used to seeing. Now, you might ask here, well, why are there two bumps if Manos is only looking at this thing over here? Well, that's probably coming from the fact that, well, we just know about a lot more objects that are big and bright. So that kind of skews what we can characterize and just gives us that second bump over there. But Manos is specifically focusing on dimmer, smaller objects. Why dimmer and smaller objects? Well, dimmer and smaller objects are pretty interesting because there's this thing that goes on in asteroid spin states where you have larger objects that kind of spin at a slow rotation speed, and then the thing is, the larger objects are typically what are called rubble piles. They're not actually like one big rock. They're more like a whole bunch of collection of rocks that are kind of held together by gravity. Now, if you spin these up too fast, they're going to start to fly apart. And then you're going to end up with smaller asteroids that are monoliths or maybe like smaller collections of rubble. But you're not going to find sort of very large asteroids that are spinning at a very, very fast rate. So we actually have what here is known as the rubble pile limit passed which there's a certain spin rate that basically you won't find larger asteroids at. In the upper left-hand corner over there, you'll find that we don't have that much data, but this is a very interesting quadrant of the plot because this is where very small asteroids exist. This is where the monoliths exist. This is where things are spinning very, very rapidly. And we don't have that much data there, which is why Manos is trying to fill in that area. So what is Manos? It's a multi-year survey that started just about last year, and it's trying to characterize small NEOs. In fact, but the thing is, it's focusing on mission-accessible NEOs. So what does that mean? It means that it's focusing on objects that we can reasonably reach with spacecraft. So things that we can actually go send a mission to, maybe do some imaging, maybe do some sample retrieval. And part of what that means is it's looking for low delta Vs, things that basically objects that can go out on conventional chemical propulsion, nothing fancy, just things that we have right now. And that's sort of the population that Manos is focusing on. One thing that I should note is that there's a regular observing cadence for Manos using telescopes from around the world, which means that overall there's going to be a huge throughput of data, a continuous throughput of data throughout the survey period, which means that you're going to have a lot of data to look at. You can kind of tackle this in one of two ways, or a combination thereof. You can send a lot of the data through grad students and have them sort of like manually type everything in and figure it out that way, or you can try to automate it a little bit and do something that's a little bit more elegant, a little bit less manpower intensive. So that's sort of what I'm trying to do here. I'm going to quickly describe what the Manos light curve data pipeline looks like. Like I mentioned before, I'm only looking at the light curve portion, not the spectra portion. So first, what happens is the Manos team gets together and they select targets and they conduct observations. And these observations can be done from a number of telescopes around the world. And then after these images are collected, we actually have software that automatically extracts which one of these many, many points of light is actually the object that we're looking at. And then once it extracts that point of light, it takes in, it analyzes that light and gets the photometry data, which is basically just how bright is that point of light at any given time. We end up with columns and columns and columns of numbers, which aren't really that sensical unless you put them in some sort of more sensical format, which is the part that I'm trying to do, which is converting the photometry data automatically into a light curve. Now, what is a light curve? Light curve is simply a plot of brightness over time. It's pretty straightforward. For asteroids, light curve is pretty important because it tells us about the rotational period of the asteroid, and it also tells us something about the shape. So let's say you have an asteroid that's kind of spherical, and it spins around, and it continues to spin around, and if it's pretty uniform, then you're pretty sad because you just get a straight line and you have no information about it. But let's say you have something a bit more elongated, like most asteroids actually are, and asteroids are often described as potato-shaped, so why a potato? So as it spins, you're going to start seeing things like, let's say this case. You're going to see a lot of the potato, and then you're going to see not much of the potato, which means that you're going to get a light curve variation that tells you a little bit about how elongated is this object. Not very elongated, you're not going to get much of an amplitude. Kind of elongated, you're going to get more of an amplitude. So this is sort of the goal of this, and what my software is going to try to convert that whole bunch of messy text over there over to something a bit more beautiful like this. So automated curve fitting, which is this first major part of this project. This, I'm going to talk about three parts of this. First is how the fitting is actually done. Second is what is actually produced from the fit software. And finally, how good the results are. Now, there are kind of two paths one can see happening when one tries to automate something that is difficult to do. The first path is where I spend a fair amount of time writing code, and then I get over this big bump of work, and then I have a lot of free time because it just starts doing all my work for me. But the other path that you could see is you write some code, debug, and then I realize that the code has now taken over my life and I have no time to write a thesis. Fortunately, that didn't happen. I'm somewhere over here. I'm a bit closer to theory. So the thesis is done. So anyway, how do we actually fit? The automated light curve fitting is done using a least squares minimization, using a model that's using Harris's Fourier series model. And this is pretty convenient because there are kind of two ways you can do this fit. One is using a command line interface. So let's say you collect a bunch of data about an object, but you don't really know much about the object. What you can do with this code is you just point the code at the data and you say, I know nothing about this object, please fit it. and it will do its best. It will make certain assumptions using the Fourier series model, and then it will give you the best result that it can. But let's say you know something about this object. Let's say you know something that says, oh, well, the object is probably has a period between like 4 to 8 hours or something like that. But then you can give the code additional information and additional parameters that you know about the object, and it can constrain the search space significantly and give you a much better result. So that's kind of a nice thing. Another really nice thing is because this whole thing kind of just runs automatically in command line, whenever Manos just collects more and more data, the code can automatically be searching the folder periodically just to say, oh, hey, you have a new object. Let's characterize it right now. So you don't really need to worry about it. Maybe you run it once a day. Maybe you run it on whatever schedule. So it's pretty convenient. You don't even really need to look at it too much. So what does it do? Takes as input this stuff, which is numbers that nobody really wants to look at too closely because it's just messy. And it gives you this instead. So this is a plot of the LISA light curve, one of the first objects I tested this code against. This is actually a pretty interesting example because this curve is actually produced from data that spanned, I believe, 4 different observing periods. And what you might get from 4 different observing periods is, well, you're going to get different offsets. So the data is actually going to be offset from each other, but you can feed that in and it can correct for that. The other thing that you're going to get is, well, you don't know what part of the period you're observing at. So you're going to have like a bunch of things from over here, a bunch of things from over here, while the periodicity might just be this. So the nice thing about this fitting method is that it sort of wraps everything around together, puts it together nicely, and phase folds the entire period so that it shows you what it actually looks like across just one period of the fitted model. Now, I should mention the bottom plot, which is the residuals of the fit. This is kind of a useful thing just to have along with it and a useful thing that the code produces, because if we see that in the residuals there's like a certain bias of a bunch of residuals being above 0, a bunch of residuals being below 0, or if we see some sort of weird curve structure in the residuals, then we might think to ourselves, well, there's probably something wrong with the fit. We probably want to mess with the parameters a little bit. And later on, we'll actually see a case where this was recently applied, where we had to do that, and we came up with a nice result after we saw that there was something messy in the residuals. So the question here is, well, how well does it work? Works pretty well, as it turns out. Initially, we tested it against 3 objects, 2012 DA14, 956 ELISA, and 2579 Spartacus. These are objects that have a lot of data behind them, a lot of observations that give them a pretty canonical, pretty well-known rotational period. And what we're going to try to do is take a very, very small subset of the data used to produce this accepted period and just feed that to the curve fitting algorithm to see what happens. As it turns out, it works pretty well. It's consistent, and within only a very, very small error for Spartacus. In that case, we're feeding it a tiny, tiny sliver of the data that was actually used to do the accepted fit. If we were to give it more data, I'm pretty confident that we'd get just consistent results throughout. So that was the portion that's automated light curve fitting. Let's move on a little bit to possibly the more interesting portion, which is the scientific question of regarding Earth encounters and NEO properties. So we're going to deal with this again in 3 parts. First is what we're comparing. Second is what we expected from the data. And third is what the data showed. So a scientific question, once again, is how does a close encounter with the Earth affect an asteroid's spin rate and shape? We're going to look at this. But first, let's look at how we're doing this. So we're comparing light curve properties to something called minimum orbit intersection distance in the NEO population. Now, I should quickly explain what minimum orbit intersection distance is. And so as part of this explanation, imagine like 2 objects. They're orbiting some central object, and you might imagine that, okay, they might pass by one another. Well, the thing is, it's really, really hard for us to actually sort of go back in time and integrate where things are going to be with any sort of precision over the course of maybe 10,000, 100,000 years, and know where the object is going to be in its orbit, because our position determination degrades significantly. Now, what is easier for us to do is to model the evolution of the orbit itself, so how the orbit of the object actually wobbles or changes over time. So we're going to use the orbit itself and figure out, okay, what if we took the orbits of two objects, say the Earth and an NEO, what is the point at which their orbits pass closest to one another? Now, what that means is we're going to be looking at lower bounds for things. We're going to, I'll briefly explain the limitations of this kind of method a bit later, but just keep that in mind, and that's the value that we're going to be using. Second, we're going to be examining NEO rotations to main belt asteroids. Now, why do that? So the NEO population, we're actually going to divide into what I'm going to call an encounter population and a non-encounter population, and we'll see how we're going to do this. But the other interesting thing that happens is, well, we know that certain NEOs will encounter the Earth. But we know that main belt asteroids are rather far away. It's pretty unlikely that any main belt object that we happen to pick will have had any sort of close encounter to the Earth just because of their orbits. So we're going to sort of treat the main belt population as a control, as a very clean sample where we don't expect any sort of encounter effects, and compare that to a population where we might expect some encounter effects. So we're comparing light curve frequency and amplitude, again, just quickly. Frequency tells us how fast an NEO is rotating, and an amplitude tells us something about the shape of an NEO. Again, remember what I mentioned about the potato, sort of longer, elongated objects, higher amplitudes, and frequency is pretty much as you'd expect. So for MOID, just from what I was saying before, smaller MOID means that there's a higher chance of an encounter. It does not mean that there has been an encounter, because we're not looking at the positions of objects, but we're rather looking at the orbits of the objects. So just keep that in mind. Sometimes you'll see objects that have MOIDs that are less than the radius of Earth. That does not mean that the object should not exist. It just means that the object's orbit might have passed the Earth, but it might be kept elsewhere in the solar system, thankfully, because of resonance or some other things, or probably there's just some error in the MOID calculation. But there aren't too many super, super tiny MOID objects, and we're probably glad for that. Again, so this means that MOID is simply a lower bound for what we think the encounter distance, the actual encounter distance of an object is with Earth. It means that there is no guarantee, thankfully, that very, very small MOID objects will actually pass really, really close to the Earth. No guarantee makes it a little bit harder for me doing data analysis, but I'm pretty sure people are glad that we don't see more of these things passing too close. So here's where I tell you that I actually pulled a bit of a bait and switch, because I talk a lot about Manos, and I talk a lot about this sort of data that we're getting from Manos. However, because Manos was started not too long ago and data is still sort of very much flowing through it, we don't have that much data from Manos. So I pulled data from the JPL Horizons database as well as the MPC light curve database. Manos data, we'll see later on, can fill in a lot of the gaps in these databases. But for the ultimate analysis that was done here, the data that were pulled were actually from MPC and JPL. So what do we expect? Well, let's think about it for a moment. We're probably, so from the literature, we found that when an asteroid encounters a planet, it sometimes gets spun up, it spins faster, and sometimes it gets spun down, it spins more slowly. But it really depends on how it is approaching the planet. If it's approaching at, I guess it depends on the spin vector of the asteroid, it depends on how the approach trajectory of the asteroid, it depends on where the planet is it dragging along, is it elsewhere? So we know that it spins things up and we know that it spins things down, but we don't necessarily know how. And given that we're observing these objects anything that we call an encounter object, we're only observing the post-encounter state of the object. We don't know what its pre-encounter state was. So that makes it a little bit harder for us to say anything about what's actually going to happen. But we do know that if it is going to spin up or spin down, then we'd expect that an encounter population of asteroids is going to have sort of a wider variation of rotational frequencies than the sort of more normal distribution that you'd expect from a non-encounter population. So we're going to be expecting a higher variance in the frequency of low MOID, meaning encounter NEOs, compared to other objects. And we might expect a higher mean amplitude for low MOID NEOs. You might think of that as being, well, as an object approaches the Earth or some other planet, it's going to get gravitationally stretched. And simulations do show that this happens, but I wasn't too optimistic about seeing this just because, well, the torques required to spin up or spin down an object are quite a bit less than the forces required to actually pull one of these things to make it more elongated. So I wasn't too optimistic about that, but I put that as something that we might see. So this was actually took a fair amount of time in my project, which is debiasing. Now, what we noticed was that there's a size and frequency correlation due to observational bias. We see that large objects are easier to see, but they also have slower rotations. Small objects are harder to see, but they also tend to have faster rotations. So we can only choose something that doesn't have this correlation, because otherwise all the data would simply show, oh, there's a correlation because of this. So what I ended up having to do was I broke up the magnitude space. So this is like the size space of the asteroids being considered. And I broke them up into half magnitude wide bins, and then searched over continuous bins and basically asked each bin, is there a correlation here? Is there a correlation here? Is there a correlation here? And I found the widest sort of bin space that I could get that didn't have a correlation. So I debiased it this way and found that I could analyze the objects that were between 24.5 and 29.5 magnitude. On the amplitude side, we're also going to have some bias issues because we might have undersampling. So what might happen is, let's say you're observing this asteroid that's rotating like this, but you only see it when it's like this. And you missed it when it's like this. And then you see it again when it's like this. So you might think, oh, well, this is a pretty low amplitude object. It's probably not very elongated. Well, that might not be true. Perhaps you're undersampling. So we pulled a debiasing procedure from Binzel and Sauter in '92. And we were able to put that together and debias that particular sample as well. So we have debiasing on both the frequency side and the amplitude side before we get into any sort of actual calculations on here. So let's talk about frequency results. Oops. What did the data show? So this is the data that we are allowed to analyze. Like I mentioned, we're not allowed to analyze anything before 24.5 magnitude, anything higher than 29.5 magnitude because of correlation reasons. So the red line here is one lunar distance. So anything before this is closer than the moon. Anything before this has a moid closer than the moon. Anything after this has a moid that is further than one lunar distance. So what does this data show? What do these data show? So how did we analyze this? So we took a 30 object moving window average. Basically, we said, okay, let's line everything up in terms of moid, and then take the first 30 objects, and then check its average and standard deviation, then throw out the smallest or the closest object and put the next object in, and so on and so forth. Keep on moving along, and you'll notice that there's this nice little drop off here. You start off with a pretty high standard deviation of frequency, so this is standard deviation only. When you have moids that are closer than the moon, you have a pretty high standard deviation. Then you hit this 1 LD moid, and then you start dropping off dramatically. And then you kind of level off here. I'm going to caution, in the frequency case, I'm going to caution any sort of results that people might be tempted to get from data points that are kind of further out, just because there's fewer data from there to actually draw conclusions from. But you'll notice that the data points here are pretty dense, and we can draw some reasonable conclusions from here. So the question, though, is, well, one lunar distance is pretty sort of arbitrary. Well, it's kind of arbitrary. So what do we mean? What do we actually mean by an encounter distance? We can't just go out to space and draw a line that says, well, any NEO that passes beyond this line has encountered the Earth, and anything that hasn't has not encountered the Earth. So we didn't do that. We did a bit more of an analysis here. And what we did was we took the NEO population and we split it up into 2 bins. The first bin was anything that was closer to the Earth than some dividing line. And we took this dividing line to be anything from 1 lunar distance to 10 lunar distances. So we did this calculation actually 10 times. And then we took the other bin to be anything past this line. Again, we did this calculation 10 times, and we're comparing these two populations. We're doing this so that we don't make sort of arbitrary assumptions about what it means to actually encounter the Earth. And we're comparing these and then taking t-test and f-test to see what happens with the mean of these two populations and what happens with the variance of these two populations. So what do we get? Well, at a dividing line of 1 lunar distance, so we're comparing a bin of objects that only have moids that are lower than 1 LD and objects that have moids of anything else, we see highly significant results in terms of the f-test. And then we start seeing we start seeing possibly significant results, and then we start seeing not so much, and then we jump back down. So what's going on here? 1 LD dividing line, probably everything in the first bin that is closer than 1 LD is pretty much, there's a pretty high probability of those objects having had some sort of encounter, at least when you have a large enough population. And then once you start moving it past that, you're going to start mixing in other objects that may or may not have lower probabilities of having those kinds of encounters. So you're going to probably start jumping up. Again, I'm going to caution against any sort of conclusions being drawn from this data set over here, just because there's not as many data points over there and not as trustworthy. Now let's look at what happened when we compared near-Earth objects with main belt asteroids. Like I mentioned, we're doing this because main belt asteroids probably have not encountered the Earth, so we're going to treat them as sort of a clean sample that haven't had any encounter effects happen. The issue is you can't just do that. You have to test only objects that are so-called equivalent, so objects that are roughly the same size. Now it's pretty hard for us to go measure these objects, so we're going to take the absolute magnitude of these objects to be sort of our size proxy. And what we notice is that we see a lot of these blue objects, which are main belt objects, that are pretty big. They're low magnitude, pretty big. And we see a lot of these sort of smaller objects that are NEOs. Well, the thing is, with smaller objects, if you have a smaller object about NEO size, maybe about this size out in the main belt, it's going to be a pretty big challenge to go see it. So we just don't have as much data on main belt objects that are smaller. So that means that our equivalent MBA NEO population has to be in a place where these two populations kind of overlap. So we're going to be looking at this section over here. What happened? Nothing significant happened. So, well, why? I mentioned before that we had this little issue with a correlation happening between, big objects having slow rotations and small objects having fast rotations. Well, if you look back over here, we were analyzing 24.5 to 29.5 objects when we were looking at the NEO population by itself. Well, when we're looking at this MBA NEO population, we're looking at a population that's quite a bit shifted over here. So we're going to start seeing that kind of results. And even if we didn't, the population sizes here are quite a bit smaller and probably not quite as good for this kind of analysis. So admittedly, nothing happened. What happened with amplitude? Well, this is the data that we're looking at. This is from MPC. And again, this is the 1 lunar distance line. These are moid values. So you're going to see a lot of objects over here that are past 1 lunar distance. You're going to see a few objects over here that are closer than 1 lunar distance. And we're going to try to do our best with the limited data set here to try to draw some sort of conclusions from it. And what do we draw? Well, we don't draw much. Because as you notice here, this is the same standard deviation plot using a 30 object moving window. And well, we actually don't get data before 1 LD. Simply because there's so little of it. So let's look at things that are further away, and we don't see very much at all. Well, why? Well, let's be a little bit more thorough first and actually put this through the same t-test and f-test and then realize that we get, again, nothing. The thing is, like I mentioned before, the forces required to torque an object are quite a bit less than the forces required to sort of stretch an object. So we need objects to have very, very close Earth encounters to have any sort of elongation effect. So, well, we don't know about as much objects as we'd like that had very, very close Earth encounters, and we probably don't want to know about, to have had too many of those anyway. But they're also just generally, in general, there are fewer of such objects that exist. So we weren't able to actually really get at the very, very close population. And again, because of the number of objects that were being examined, here I'd caution any sort of conclusions that people might be tempted to draw from this data set on this end of the plot. It's because very, very few objects being considered. So conclusions and future work. Let's quickly go back over what just happened. Manos can now automatically characterize light curve data. Pretty nice. And it recently characterized 2014 HW, which is actually an object that was actually one of the smallest and fastest rotating objects ever observed, which is pretty awesome. This is actually one of the plots that I mentioned before, where we actually had to do a little bit of intervention because typically the software that I developed makes certain assumptions about the Fourier series that we're supposed to fit to it. But we found that this object was a little bit unusual, so we had to actually go in, modify the parameters a little bit, and then find that, well, it actually fits pretty nicely. And we don't get any sort of structure or bias, really, from the residuals, and that probably means that it's fitting pretty well. Back to the scientific question, we found that there's a highly significant difference shown between objects with Moid values of less than 1 lunar distance and objects that are at a Moid value of greater than 1 lunar distance. And we found that, well, that makes sense because Earth encounters can either spin up or spin down an object, which means that there's going to be a wider variation of the distribution of frequencies, but there's not necessarily going to be a change in the mean because just because you're spinning up or down doesn't mean you're going to change the average. We didn't find an overall trend in frequency, again, because the average is probably going to stay about the same. The NEO-MBA comparison didn't show a significant difference in frequency because we didn't really have that many objects to look at. We only had 11 objects that with Moid of less than 1 LD, probably not a sufficient data set. However, should consider the fact that, hey, things that are pretty close to the Earth and sort of small objects are would probably fall within at least some portions of what Manos is actually targeting. So once the Manos pipeline gets up and running and we actually get more data, we'll actually probably get some of our gaps in our data actually filled in, which will be nice when we do future analyses. For future work, I've identified a number of improvements that can be put in the software, things that make it so that you can feed even more data into it if you know a lot about the objects that you're trying to characterize, or if you know even less than anything, then we'll be a bit more robust about that. We'd like to incorporate the Manos data, obviously, so that I don't have to do that whole bait and switch thing. And we'd like to use integrated instead of instantaneous Moid, because right now our Moid calculations are figured out basically by the current orbital parameters of the object, but we could kind of evolve these orbits back into the past and see, well, what's a better sort of Moid value for the Earth and whatever NEO that we want to consider. So that'll give us a bit more precision on these numbers. It's a lot of numbers to look at to crunch through, though. And finally, we want to do a little bit of simulation work on encounter effects. So the hypothesis for this thesis was drawn from simulation work, but it was done sort of for objects well, only a few objects, and objects that are passed by very, very close to the planet. We realize now that even at sort of encounter distances of up to 1 lunar distance away, we might still see effects on the physical properties. So we might try to consider thinking about objects having encounters that actually are a bit further away and see what happens physically with their spins, what happens to their shapes, and so on. And maybe what it takes to actually elongate an object. So I'd like to thank my thesis advisors, Professor Rick Binzel and Dr. Nick Moskovitz, who isn't here right now. And I'd also like to thank Dr. Amanda Bosch and Alyssa Earle for 2014 field camp, which got me started on a lot of this. And finally, communications instructor Jane Connor, without which all of my data would be singular.